Electrical Circuits and Networks Introduction to Electrical Circuits and Networks. Hello folks, welcome to today's lecture on electrical circuits and networks. In the realm of electrical engineering, a foundational understanding of electrical circuits and networks is crucial. These systems form the backbone of virtually all electronic devices that power our modern world. Whether in communication systems, industrial automation, or consumer electronics, circuits and networks are integral. Introduction to electrical circuits and networks. What are electrical circuits? An electrical circuit is a closed path allowing the flow of electrons from a voltage or current source. It consists of various electrical components like resistors, capacitors, inductors, diodes, and transistors interconnected by conductive paths, usually wires. The primary purpose of a circuit is to transport electricity to perform work such as lighting a bulb, driving a motor, or amplifying a signal. Components of electrical circuits. Resistors, these impede the flow of current and are used to control the voltage and current within a circuit. Resistors are crucial for protecting sensitive components from high currents. Capacitors, components that store and release electrical energy in a circuit. They play a vital role in timing applications and filtering noise from signals. Inductors, these store energy in a magnetic field when electric current flows through them. Inductors are commonly used in power supplies and radio frequency applications. Diodes, components that allow current to flow in one direction only, essential for converting AC alternating current to DC direct current in power supply circuits. Transistors, semiconductors used to amplify or switch electronic signals, forming the building blocks of modern electronic devices. Understanding circuit analysis and design. An electrical network is a more complex system that may consist of multiple interconnected circuits. Networks are used in various applications ranging from the national power grid to telecommunication systems. Understanding networks involves analyzing how energy is distributed across different branches and how signals propagate through the system. Circuit analysis techniques. The analysis of electrical circuits involves understanding how the components interact and predicting their behavior under different conditions. Several techniques aid in this process, including Ohm's law. This fundamental principle relates voltage V, current I, and resistance R in a circuit. V equals I times R. Understanding this relationship helps predict how changes in one element affect others. Kirchhoff's laws, these include Kirchhoff's voltage law KVL, which deals with the sum of voltage drops around a loop, and Kirchhoff's current law KCL, which concerns the sum of currents entering and exiting a node. Mesh and nodal analysis. Mesh analysis involves writing KVL equations for independent loops, while nodal analysis uses KCL to analyze the nodes of a circuit, providing a systematic way to solve circuit equations. Designing electrical circuits. Designing an electrical circuit involves specifying the components and their arrangement to accomplish a specific task. This process requires a deep understanding of electronics principles and practical experience. Here are some key considerations: purpose and requirements. Define what the circuit needs to achieve, such as amplifying a signal or regulating voltage. Understand the constraints like power consumption and size. Component selection. Choose appropriate components based on the desired specifications, such as selecting the right resistor value to limit current adequately. Simulation. Use software tools to simulate the circuit's behavior before physical implementation, helping to identify potential issues early. Prototyping. Build a prototype to test the circuit in real-world conditions, allowing for adjustments and improvements. Executive summary. Here's a summary of electrical circuits and networks. Types of electrical circuits. 1. Series circuit. A circuit where components are connected one after the other and the current flows through each component in sequence. 2. Parallel circuit. A circuit where components are connected across each other and the current flows through each component independently. 3. Combination circuit. A circuit that combines series and parallel connections. Components of electrical circuits. 1. Resistors. Components that oppose the flow of current measured in ohms omega. 2. Capacitors. Components that store energy in an electric field measured in farads F. 3. Inductors. Components that store energy in a magnetic field measured in henries H. 4. Voltage sources. Components that provide a constant voltage, such as batteries or generators. 5. Current sources. Components that provide a constant current, such as current regulators. Network analysis techniques. 1. Ohm's law, a fundamental law that relates voltage, current, and resistance in a circuit. 2. Kirchhoff's laws, a set of laws that describe the behavior of currents and voltages in a circuit. 3. Nodal analysis, a technique used to analyze circuits by applying Kirchhoff's laws to each node. 4. Mesh analysis, a technique used to analyze circuits by applying Kirchhoff's laws to each loop. 5. The Venon's theorem, a technique used to simplify complex circuits by replacing them with a single voltage source and series resistance. Circuit theorems and laws. 1. Superposition theorem, a theorem that states that the response of a circuit to multiple sources is the sum of the responses to each source individually. 2. The Venon's theorem, a theorem that states that a complex circuit can be replaced by a single voltage source and series resistance. 3. Norton's theorem, a theorem that states that a complex circuit can be replaced by a single current source and parallel resistance. 4. Maximum power transfer theorem, a theorem that states that the maximum power is transferred from a source to a load when the load resistance is equal to the source resistance. Network topologies. 1. Star topology, a topology where all devices are connected to a central node. 2. Bus topology, a topology where all devices are connected to a single backbone cable. 3. Ring topology, a topology where devices are connected in a circular configuration. 4. Mesh topology, a topology where each device is connected to every other device. Applications of electrical circuits and networks. 1. Power systems, electrical circuits and networks are used to generate, transmit, and distribute electrical power. 2. Communication systems, electrical circuits and networks are used to transmit and receive information. 3. Control systems, electrical circuits and networks are used to control and monitor industrial processes. For electronic devices, electrical circuits and networks are used in a wide range of electronic devices, including computers, smartphones, and televisions. Here's a summary of understanding circuit analysis and design. Introduction to circuit analysis. 1. Circuit fundamentals, understanding the basic concepts of circuits, including voltage, current, resistance, and power. 2. Circuit elements, familiarity with circuit elements such as resistors, capacitors, inductors, and sources. 3. Circuit laws, understanding of circuit laws, including Ohm's law, Kirchhoff's laws, and the Venon's theorem. Circuit analysis techniques. 1. Nodal analysis, a method for analyzing circuits by applying Kirchhoff's laws to each node. 2. Mesh analysis, a method for analyzing circuits by applying Kirchhoff's laws to each loop. 3. The Venon's theorem, a technique for simplifying complex circuits by replacing them with a single voltage source and series resistance. 4. Norton's theorem, a technique for simplifying complex circuits by replacing them with a single current source and parallel resistance. Circuit design principles. 1. Design specifications, understanding the requirements and constraints of a circuit design, including voltage, current, power, and frequency. 2. Component selection, choosing the right components for a circuit design, including resistors, capacitors, inductors, and sources. 3. Circuit topology, selecting the right circuit topology, including series, parallel, and combination circuits. 4. Circuit optimization, optimizing circuit performance, including minimizing power consumption, maximizing efficiency, and reducing noise. Circuit analysis tools. 1. Circuit simulators, software tools such as SPICE that simulate circuit behavior and allow for analysis and design. 2. Circuit analyzers, hardware tools such as oscilloscopes and multimeters that measure circuit parameters and allow for analysis and troubleshooting. 3. Circuit design software, software tools such as CAD programs that aid in circuit design and layout. Circuit design considerations. 1. Power consumption, minimizing power consumption to reduce heat, increase efficiency, and prolong battery life. 2. Noise reduction, reducing noise and interference to improve circuit performance and reliability. 3. Component tolerance, considering component tolerance and variation to ensure circuit performance and reliability. 4. Scalability, designing circuits that can be easily scaled up or down to meet changing requirements. Advanced circuit analysis and design topics. 1. Frequency domain analysis, analyzing circuits in the frequency domain to understand their behavior and performance. 2. Time domain analysis, analyzing circuits in the time domain to understand their behavior and performance. 3. Nonlinear circuit analysis, analyzing circuits with nonlinear components such as diodes and transistors. 4. Digital circuit design, designing digital circuits, including logic gates, counters, and registers. Conclusion: mastering electrical circuits and networks is essential for any aspiring electrical engineer. These systems are not only fascinating due to their complexity, but are also indispensable in advancing technology. Whether designing a new electronic gadget or managing power distribution, a solid grasp of circuits can lead to innovative solutions and efficiency. Thank you for joining this lesson on electrical circuits and networks. We hope to see you in the next lesson. Happy learning, folks!